All right, good morning, everyone. We might as well start our lecture. So today we were starting a new topic on fluids. So far since the beginning of the course, especially when we talked about motion, we started describing how an object moves, and then we went on to forces and then rotational motion. So up to this point, we were only considering like solids. We considered objects that are solids, we made them move, and then we described their motion. And that's because in general, solids are not easily compressible. Of course, they are deformable, like we've learned last time when we talked about elasticity, stress, and strain. But in general, we can consider many solids to be rigid and not compressible. And that simplified our analysis of kinematics and motion. But matter also exists in different forms. It also exists as liquids and gas, and there's a fourth form, the plasma, which is the ionized state, but we will not consider plasmas in this course. So in general, we'll consider only liquids and gases. And liquids and gases, they are different from solids because liquids and gases, unlike solids that are rigid, liquids and gases flow easily. And since they both flow easily, we collectively call them as fluids. So when we say fluids, we're not just talking about water or liquids. We're also referring to gas as well. So in the remainder of the course, we will be talking about fluids. This week, we will focus more on liquids, and then later on in the course, we will look at gases. All right, so today we will start our discussion on fluids, and what we will learn when we talk about fluids are these things. So first, we will define quantities that better describe fluids in terms of density and pressure. And then pressure is related to buoyancy, which is essentially the force that a fluid exerts on an object. And we'll talk about buoyancy in lecture 23 in tomorrow's lecture. But first, in this, when we're talking about density, pressure, and buoyancy, in the beginning, we're just considering that the fluid is not moving, meaning the fluid is static. But later on, after we've learned about fluids that are not moving, we will then learn about fluids that are flowing, that are moving, because in general, fluids don't really just stay stationary, right? They move, air molecules move, water flows, for example. And so we'll also have to consider fluids that are moving, and that's the object of fluid dynamics. And so in lecture 24, our lecture on Wednesday, we will talk about continuity equation and Bernoulli's equation to describe fluids that are moving. But for today, our goal is to learn about the quantities, density, and pressure to describe a fluid. What are these quantities? What affects pressure? What is this term called relative density? And so that's our goal for this lecture. Right, so for density, let's just go back to what we already know. When we were talking about solids, we usually quantified solids in terms of their mass. Right? And so when we were talking about moving objects, like momentum or kinetic energy and all this stuff, we were talking about the mass of the object. But if we're talking about fluids, they flow easily. So usually you need a container to contain the fluid. And so instead of mass, density will be a more useful quantity to describe fluids because it takes into account the volume of the container that contains the fluid. So density is defined as mass divided by volume, and its unit is kilogram per cubic meter or kilogram per meter cube. So because you are dividing mass with volume, density becomes a property of a material. So this table, for example, shows you the densities of different materials. Say, for example, if you look at the density of water, which is about 1,000 kilograms per cubic meter, what the density of water means is that in a volume of 1 cubic meter, 1,000 kilograms of water can be contained in such 1 cubic meter of volume. Right? So density is always a measure of the mass divided by the volume of the material. So I'm just housekeeping here. So we use this symbol to describe density. This is not P. This is the Greek symbol rho. Okay, so we refer to rho as the density of the material. It's of course mass divided by volume. Density, aside from being a property of the material, which you can look up in a table such as this, density also defines the sinking and floating of an object. And we will talk about sinking and floating in the next lecture. But in general, when we talk about buoyancy, but in general, objects with higher densities sink under objects with lower density. So the density of the material determines whether it will float or sink. And the concept of sinking or floating, if we just analyze this statement here, higher density sinks under lower density. To determine sinking and floating, we're sort of comparing the densities of two materials or to fluids, right? And so if we're comparing the density of two fluids, specific gravity or relative density is the quantity that compares the density of one fluid to a reference fluid. And usually the reference fluid is water. So if we put the definition of specific gravity into an equation, we have this equation for specific gravity. It's really just comparing the density of a material to the density of water, which is 1,000 kilograms per cubic meter. Right, so say for example, the density of the material, if the density of the material is greater than the density of water, then if we work out this equation here, then the specific gravity will be greater than 1. And therefore, the material will sink if you put it on water. Okay. On the other hand, if the density of the material is less than water, okay, then the specific gravity will be less than 1. And in such case, materials that have smaller densities will float over water. But really the key idea here is specific gravity compares the density of the material to the density of water, and determines whether that material will sink or float when placed in water. Let's just look at an example of how specific gravity is often used. So here you have 500 milliliters or ml. So this is a measure of volume. Yeah. Liters or milliliters is a measure of volume. 500 milliliters of a substance has a specific gravity of 9.8. We want to find what is the mass of this substance having a specific gravity of 9.8. The density of water is 1,000 kilograms per cubic meter, which is, you will encounter this density quite a lot, so it might be something useful to write down in a formula sheet if you're building one. Right, starting from the definition for specific gravity, we're comparing the density of a material, which is the substance we're after, to the density of water. What we know, we're given the specific gravity, it's 9.8. The density of water is sort of a constant that you can look up in the table. We are then able to determine what's the density of the substance by multiplying the specific gravity and the density of water. Okay. Then once you've determined the density of the substance, which is 9,800 kilograms per cubic meter, what we're after is the mass. The mass is related to the density of the substance via the definition density equals mass over volume. That allows us to find the mass knowing the density and the volume of the substance. The volume is of course given 500 ml. Okay. Right. So just have to convert 500 ml. So this thing here is the conversion from ml to cubic meter, or you can use the conversion factor ml is equal to 10 to the minus 6 cubic meter, which then gives you the conversion factor liter is equal to 10 to the minus 3 cubic meters. So I would say these are important conversion factors because often you're given volume in milliliters or liters, but the SI unit for density requires you to have cubic meters as the unit for volume. Right? So you will be converting often milliliters to cubic meters or liters to cubic meters. So just remember to convert your volumes to cubic meters. Converting 500 milliliters will give you the correct mass, 4.9 kilograms. Right. Be happy with that solution. So far, what we've done so far is define what density is and define what specific gravity is. Now, when the fluid is contained in a container, right? So imagine a balloon which has air inside, then the air molecules are free to move, easily move inside the balloon, but as they move, they bump the surface, as the air molecules are moving inside the balloon, the air molecules sort of bump the surface of the balloon. So the air molecules exert force on the surface of the balloon, right? So in general, fluids, when they're inside a container, they exert force on the surface of the container that contains them. But instead of just describing the force that the fluid exerts, pressure will be a more useful quantity to describe the force that the fluids exert on the container, because pressure also accounts the area over which force is being exerted. So pressure is defined as the force exerted by the fluid per unit area of the container surface that contains the fluid. Just some housekeeping again, the SI unit for pressure will be newtons per meter squared, following from the definition of pressure being force divided by area. Unit for force is newtons, unit for area is meter squared. Hence, unit for pressure is Newton per meter squared, but that has a special name, which is the pascals. So Pascal is, PA also gives you the pressure, which is the SI unit for pressure. Right, so what this equation means is that the pressure is directly proportional to the force, meaning for a fixed area, the bigger the force, the bigger the pressure is exerted on the surfaces of the container. And of course, the smaller the force, the smaller the pressure. Okay. The pressure is, however, inversely proportional to the area. Okay, notice how the area is in the denominator. So that means pressure is inversely proportional to the area, meaning for a fixed force, if you're applying a fixed amount of force, the bigger the area, the smaller the pressure, and the smaller the area, the bigger the pressure. So inverse proportionality relationship there, right? Okay, so going back to the balloon again. Right, so I have here a single nail. The fluids in the form of gas is contained inside the balloon, right? So single nail, the area is just the tip of the nail, right? Okay, put the balloon, probably doesn't do anything, right? You have pressure being force over area. The force is force exerted on this small area is coming from the weight of the balloon, which is probably not enough to do anything else. But if I push down, say using this, put this on top of the balloon, so the weight of this board will now provide the force. You ready? You probably know what to expect, right? There you go. It's a good way to wake us up in this gloomy day, right? So very small area, the tip of the nail, right? What will happen if I have, instead of a single nail, I have here a lot of nails. Again, put the balloon there, right? Area, it's this whole area here with all the nails. The force will come from the weight of the balloon, which is again not enough to do anything else. I'll use again the weight of the board to exert the force. Right. Ready? Right. And doesn't really do anything. So so we can dramatically see the effect of the small area of a single nail compared to the larger area of this collection of nails here. In fact, we can even squeeze and we can, you want to find out how much force. Don't want to wake up. Yeah, and yes, you kind of sort of squeeze quite a bit, right, to accomplish the same effect. That means, you know, over a large area, you need to apply, over a large area, you need to apply a bigger amount of force to accomplish the same amount of pressure that will pop the balloon. Cool. All right, so pressure does not only depend on force, but also the area. Okay, now before we go further and analyze pressure in fluids, let's look at this example that uses a solid. I guess easier to visualize solid. So I'll use this example of the high heels, the stiletto heels, to demonstrate the relationship between force, area, and pressure, and because this will then be related to fluids. So let's look at this example. So a female with a mass of 45 kilograms wears stilettos with an area of 1 centimeter squared. Okay, so 1 centimeter squared on each heel, a very small area. Of course, on this part here, you have a larger area. That's the toe area, which has a bigger area than the stiletto heel. Calculate the pressure exerted on the ground by the spike of the heels, assuming that half the weight of the person is on the spikes and the other half is on the front soles. Okay, the same problem there. I've just rewritten it with more space here. So pressure what we want is to find the pressure, and pressure is defined as force divided by area. The question is, what is the force? Here, the force is, of course, provided by the weight of the person who is standing on the stiletto heel. Okay? So the force exerted on the heel and therefore on the ground is provided by the weight. The problem says half of the person's weight is on the spikes of the stiletto, and therefore it's mass divided by 2 times G. That will give you the force, which is half the weight that's exerting on the heels. The area, that amount of force, half the weight, is being exerted on the stiletto heel with area of 1 centimeter squared. Again, convert your areas to square meters. Okay. For consistency of units, that gives you a pressure of 1.1 times 10 to the 6th Pascal. So that is quite a significant amount of pressure. Times 10 to the 6th means about 1 million pascals of pressure. And so that's why stiletto heels can be quite deadly. I don't know if the TV series CSI is still popular, like crime scene. There was one episode where they were investigating the death of the murder using a stiletto heel. It can exert, it sort of like acts like a single nail, right? You have a very small area and exerting some force can have enough pressure. So which object would you rather step on your toe, stiletto heel with a very small area, or the tire of a car with a wider area? But this is probably a hypothetical question, right? It also depends, because the mass of a person is much less than the mass of a car. But I'll leave that hypothetical question up to you to debate on. Right. But yeah, so pressure, force over area. In this particular example, the force was provided by the weights of the person distributed over that area. Now, if we think about fluids and the atmosphere, we are actually living at the bottom of an ocean of air, right? So if this is Earth, the ground, then there's atmosphere, surrounding us all around. And so, of course, air molecules have mass. And so the weight of the column of air above us exerts pressure on our head, for example, right? So the pressure of air molecules in the atmosphere exerts pressure on the surface of objects. And we call this pressure the atmospheric pressure. Very intuitive, right? Because it's the pressure being exerted by the atmosphere on the surface of objects. So if we look at the atmosphere, if we go very high where there's very few air molecules, then the pressure at a high altitude is very small. Okay, we can consider it to be negligible if we're really up high up there, almost in outer space. And as we increase the depth, okay, as we go down to the ground, there's more and more air molecules above us, and so the pressure increases because there's more force being exerted per unit area. Okay, when you are at the surface of water, say at sea level, then the weight of air pressing on an area of 1 meter squared is about 101.3 kilonewtons. Okay. You can sort of measure that. And so at the surface of the water at sea level, here, surface of the water here, the pressure is about 101.3 kilonewtons per meter squared, or 101.3 kilopascals, which we call as 1 atmosphere. So at sea level, the amount of pressure exerted by the air molecules on an area of 1 meter squared is equal to 1 atmosphere, and 1 atmosphere is equal to 101.3 kilopascals because that's the amount of force in newtons per 1 square meter of area being exerted at sea level. And of course, the deeper you go, say if you go swimming around here, then you will experience more pressure, because aside from the pressure exerted by the air molecules, you also have pressure exerted by water above you. Okay, so using this reasoning, we can then write the total pressure experienced by objects under fluids by this equation here, P equals P0 plus rho GH. So let's define what each of the terms in this equation means. So P, this is the total pressure at some depth H. Okay. So notice we are using depth instead of elevation. Okay. So P is the total pressure at some depth H. It's also called the absolute pressure. Okay. So when you read the term absolute pressure just means total pressure, okay, at some depth H. P0, that's the pressure at the surface. Okay. So from our analogy here, that's P0 is the pressure at the surface of the water here, and that will be, if the surface is water, then P0 will be the pressure of the atmosphere pushing down, in which case that is the atmospheric pressure, 101.3 times 10 to the 3 pascals. Right. And if you go deeper under the surface of the water, then you also have to consider the height, the depth for which you are under the surface of water. And so you have this term plus rho GH, this term plus rho GH, and that term plus rho GH is what is called gauge pressure. So gauge pressure measures the pressure due to the weight of the fluids above the objects but below the surface of the liquid. So rho, of course, is the density of the fluid. Right. So if we go back to this scenario here, so if you're just at the surface of the water here at water level, then the pressure, the total pressure or absolute pressure you're feeling will just be equal to the atmospheric pressure, 101.3 kilopascals. But if you go under the surface of the water at some height H, then the absolute or total pressure that you're feeling there will be the pressure of the atmosphere above the surface of the water plus the pressure exerted by the water molecules above you, which is from the weight of the water molecules. Okay. So at a certain depth H, you have to include this plus rho GH term. All right, so does this equation sort of make sense? Because this is sort of the foundation. Understanding what this equation means and what each term means is the foundation of what will happen, what we'll discuss next. And so to emphasize this equation, let's look at an example first. So the question is asking, at what depth in water would you experience a pressure of 2 atmospheres? All right, so so the scenario is you go swimming, this is the surface of the water, and you're at some depth. You want to find what is this depth so that the pressure that you experience, meaning the total pressure or absolute pressure, is 2 atmospheres at this depth that you're swimming. Okay. Right. Of course, there is the water surface here. Okay. Yeah. So of course, there is the water surface here. So above you, there are air molecules exerting pressure on the surface of the water. So that is this P0 here. Okay, and then you have this extra height, extra depth, where you have water molecules above you exerting this extra gauge pressure rho GH. Okay. So what do we know? The density of water, it's 1,000 kilograms per cubic meter. So we know in the given, what's given is that the total pressure where you are at is 2 atmospheres. Okay, that's the total pressure here, or absolute pressure. There we have to convert our pressures to pascals because that's the SI unit. So for, yeah, right, it's quite crucial to convert to pascals. And we have the conversion factor, 1 atmosphere is equal to 101.3 times 10 to the 3 pascals for the conversion factor. And hence 2 atmospheres is 2 times 101.3 times 10 to the 3. Right, what else do we know? This P0, this is the pressure at the surface of the water. That's pressure exerted by the atmosphere on the surface of the water. That's atmospheric pressure, 101.3 times 10 to the 3 pascals. Okay. Right, we then rearrange this equation because we're after the depth, H, how deep you are, right? You have here the pressure where you are located, pressure at your depth, 2 atmospheres converted to pascals, minus the atmospheric pressure at the surface of the water divided by the density of water times G. Right, are we happy with how to interpret this equation? Okay, so this equation really, if you look at it, then the total pressure really just depends on the depth, H. It doesn't really depend on the size or the shape of the container. Okay, so say you have these different vases of different shapes, and you want to find the pressure at this point, which is the same depth at same depth for each of the vases with different pressures. This will be the pressure at this depth here. The pressure here will be equal to, as given, P0 plus rho GH. Okay, so for each of these vases, they have an open end. So here at the open end, you have the air molecules exerting atmospheric pressure. This will be P0 in this equation here. Okay, so for each open end here, the atmosphere is exerting a pressure equal to the atmospheric pressure, 101.3 kilopascals. Okay. Right, and it's the same atmospheric pressure being exerted on the surface of each of the vases. Right? Because, yeah, look how the surfaces are all at the same height. So it's the same atmospheric pressure being exerted on the surface of each of the vases. So P0, this is equal to the P atmosphere, which is the same for all vases. So really what's different, what can change is the height. So if you are measuring the total pressure at the same depth H, then this term rho GH will also be the same. And assuming that it's the same fluid or it's the same liquid in all the vases, the density does not change, then therefore the pressure at the same depth should be the same regardless of the shape of the vases. Okay? As long as the depth is the same, you're measuring the total pressure at the same depth, then the pressure at each of these points at the same depth should be the same. Does that make sense? Right? Okay, so since pressure only depends on depth and not on the shape, pressure can therefore be measured by looking at how the depth of a fluid changes. And this is exactly how the barometer and the manometer, which are two instruments used to measure pressure, operates. The operation of the barometer and manometer really relies on the fact that the total pressure depends on the depth of a column of fluid within them. And so let's look at the details of both the barometer and the manometer to see how this equation applies to the measurement of pressure. Right? So let's look first at the details of the barometer. So the barometer is a device that measures atmospheric pressure. What the barometer is you have a dish. It's an open dish that's filled, usually it's filled with mercury. And then you have a column, like a tube. You have a tube that is inverted onto this container of mercury. So some mercury from the open container will rise into the tube up to a certain height H. Okay? And we want to measure the pressure of the atmosphere that's pushing on the surface of the open container filled with mercury. So we know that the pressure at this depth, okay, the pressure at this depth, this is the pressure that we want to measure, the pressure of the atmosphere. The pressure at this depth will depend on the pressure at the surface of the liquid of mercury plus the gauge pressure, which depends on how much pressure the weight of the mercury in the column is exerting on the mercury on this container. Okay. But the pressure at the surface of the mercury here will be 0 because there's nothing inside the column. How do you stop this thing? Okay, yeah, there we go. Sorry about that. Someone's calling me in Teams. Right, so where are we at? So we want to measure the pressure of the atmosphere, which is the pressure at this height, at this depth here. So using this equation, we need to know the pressure, yeah, P0. P0 is the pressure at the surface of the mercury, which is this pressure here. This is P0 over here, but at this point, there's nothing inside the column here. It's empty, it's a vacuum, and so the pressure there will be equal to 0. So the pressure at this depth here, where we want to measure the atmosphere, will just depend on the weight of the mercury in this column, which is equal to the gauge pressure rho GH. The pressure on the pressure of the atmosphere, okay, at this depth will therefore be equal to the density of the mercury times gravitational acceleration times the height of mercury. Okay. Now, assuming that the pressure of the atmosphere is equal to 1, okay, so if we assume that the pressure of the atmosphere at this depth here is equal to 1, okay, and the density of mercury is, of course, a property of the mercury we can look up, then we are able to calculate the height of the mercury column in this tube. Right. So the height of the mercury column will be 0.76 meters or 760 millimeters, which tells us that if you, so there should be some scale here, height scale, that measures the height of mercury in the tube. If the height of the mercury in the tube is 760 millimeters or 0.76 meters, then we know that the atmospheric pressure is 1 atmosphere, because 1 atmosphere of pressure on the surface of the mercury in this container will result to a height of 0.76 meters on the tube. Okay. And so any change in the atmospheric pressure will result to a change in the height of the mercury column. So by measuring the change in height of the mercury column in the tube, we will be able to deduce or figure out what's the pressure of the atmosphere here, using the reference where if the height of the mercury in the tube is 760 millimeters, then the pressure of the atmosphere should be 1 atmosphere. Okay. Does that make sense? Yeah.
Is there a barometer that's always like?
Yeah. Yes, there's always a column, and so it only goes like 760 millimeters, and it's one of the reasons why in a barometer mercury is used, because of its high density. Yeah, its high density means that it doesn't need to go so high to measure 1 atmosphere. If you were to use, in the next example, we'll see what will happen if you use water. How high, how long the barometer has to be if instead of using mercury, you'll use water. Yeah, so that's how the barometer measures atmospheric pressure. It's through the height of the mercury in this tube or in this column. Right. Okay, so yeah, as I've mentioned, let's look at, just before we go to that example. So from here, we saw that if the pressure at the atmosphere is 1 atmosphere, then the height of mercury in the tube will be 760 millimeters. So 760 millimeters of mercury equals 1 atmosphere, and that's why millimeters of mercury is also used as a unit of pressure, because it gives you a reference point for 1 atmosphere. So there are different units for pressure that you might encounter as you read the textbook or the internet or read problems. But pascals, this is the SI unit. So you will always have to go back to pascals, and you'll always have to convert these different pressures into pascals, because pascals is the SI unit. And here I summarize the conversion factors for the different units of pressure that you might encounter. All right, so that aside, let's look at this example. It's a very similar concept to how the barometer works, but this time it's water. So water in a glass. right? So when you drink water from a straw, you create a pressure difference between the surface of the water and your lungs. And the glass of water is approximately at atmospheric pressure, because if this is the surface of the water, then you have, of course, atmospheric pressure on the surface. So the glass of water is approximately at atmospheric pressure. But by expanding your lungs, you decrease the pressure in your lungs, and that creates a pressure difference between your lungs and the surface of the water. So say, for example, this one goes into this end of the straw goes into your mouth and say in your lungs. So the pressure at this end will be equal to the pressure of your lungs. And assuming that you could achieve a pressure of 0 atmosphere in your lungs, which is sort of impossible, because that means there's no more air in your lungs, which will then cause you to pass out. Yeah, but for simplicity, let's just assume that you're able to achieve pressure of 0. So it's very similar to the barometer. Instead of mercury, it's now water. The question is, what is the longest straw that you can drink water from? So what will be this height, so that water from the glass is still able to rise up because of the pressure difference between the atmospheric pressure on the glass and 0 pressure in your lungs. Okay. Right, so similar approach as before. You're creating 0 pressure here. So the height will just depend on the atmospheric pressure, which is 101.3 times 10 to the 3 pascals. The density of water is 1,000 kilograms per cubic meter, and G's, of course. And that will give you a height of 10 meters. So if you have a 10 meter straw, well, this is the ideal case, right? You can make the pressure in your lungs 0. But this makes the case that if you were to use water instead of mercury to construct your barometer, then you'll need a very long tube in order to measure 1 atmosphere. You'll need at least 10 meters or more, more than 10 meters of tube in order to measure 1 atmosphere. Cool. Right, does that make sense? Or is it making sense so far? Right. Okay, the other measurement instrument used to measure pressure is the manometer. So the manometer looks like this. It has a closed end. Okay. The closed end is where the pressure that you want to measure is. And then it has an open end. The open end is, of course, exposed to the atmosphere. And you have liquid inside the tube. The pressure is related to the depth of the liquid. So on the open end, that's exposed to the atmosphere. So you have atmospheric pressure on the open end here. The closed end is where you want to measure the pressure. And so at the surface of the liquid near the closed end, the pressure will be P, the pressure that you wanted to measure. Of course, the pressure here in the open end is atmospheric pressure. So you want to measure the pressure at this level, at this depth. Okay. We said that pressure depends only on depth. So the pressure at this depth here at the closed end should be equal to the pressure at this depth in the open end, right? They're at the same depth. So pressure at the same depth is the same. So if you wanted to measure the pressure here, okay, at the closed end, that's equivalent to finding the pressure at this point at the open end at the same depth as where you want to measure the pressure from. Okay. So as usual, the total pressure here at this depth, the total pressure at this depth will be equal to the pressure exerted by the atmosphere on the surface at the open end, plus how much pressure is exerted by this much fluid above this depth where you want to measure. Right. So the pressure at this depth will therefore be atmospheric pressure 101.3 times 10 to the 3 plus the gauge pressure, which depends on how much this depth is. So the manometer operates by using the difference in the height in the liquid between those the open and the closed ends. Rho GH is, of course, what we call gauge pressure. So let's just look at this and let's put numbers to sort of see how the manometer works. So this is an idealized manometer. You have a closed end and an open end. It's filled with water. So the liquid inside your manometer is water. Determine the pressure at the top of the closed end of the tube. So you want to find the pressure here at the closed end. Which is 40 centimeters from the base, and this whole column of water here is 100 centimeters. So we want to measure the pressure here. We know that the pressure at the closed end should be the same as the pressure at this depth, right? Because they're at the same depth. So to find the pressure at the closed end, all we need to do is to find the pressure at this depth in the open part of the tube. The pressure here will depend on the pressure of the atmosphere exerted on the surface of the water here, which is 101.3 times 10 to the 3 plus the gauge pressure rho GH, where H is equal to 60 centimeters. So the total pressure at this depth here is equal to the pressure of the atmosphere plus how much pressure this weight of water exerts at this point here. So you have atmospheric pressure plus the gauge pressure that depends on the height of the liquid column above that point where you want to measure the pressure. So that gives you the pressure at this point, which should be the same pressure at the closed end of the manometer because they are at the same depth. Right, does that make sense? Okay, right, so what we've learned today is that when we're talking about fluids, densities, mass over volume, the fluid exerts pressure, which is equal to force over area, but pressure depends mostly on depth. If you have a surface, then the total pressure should be the pressure at the depth plus the pressure exerted by atmosphere at the surface of that liquid. Right. And so that ends our lecture for today. Tomorrow we will talk about buoyancy, which will be a consequence of pressure, still consequence of pressure on fluids. Right, so have a good day, everyone, and I'll see you tomorrow.